provide some material to motivate you again, because it's a new week. And I'll show you what my doctoral student sent a couple of days ago. She's working on a multi-robot trajectory planning. So imagine an Amazon warehouse. So you have many robots moving back and forth, collecting items ordered, bringing it to a packaging center. I don't think they can package yet because the finger, you need good finger dexterity. And also delivering to the docks and so on. It's a very complicated operation, and they say that by 2030 Amazon will have more robots than human beings. So let's watch that video. I have to find it first. Here it is. So a multi-robot, 3 robots, right? Some starting location and some destination. The 3 of them have. And the idea is not to collide with each other, but you can not collide with each other and create a horrible path. Very slow, stop. Whenever you see anything moving, stop, wait for the moment to die down, and then go forward. That won't be optimal because Amazon wants to move products. In fact, some of their workers have mentally collapsed with the pressure on them to package a certain number of parcels per hour. They can take a 5-minute break, but then they're back again. It's repetitive motion. It's not fun to do. So robots will obviously not break down, but then the human being needs a job. So that is the battle going on. Like you would rather have a job that is stressful than no job at all, right? Most of us would at least like to have a job which is stressful. So that's what she has done. Okay, it's showing up here. I will move it there. So this is in the interior side of our building, which is an open area about 45-50 meters by about 30 meters. So there are 3 robots, and deliberately she is pointing them this way, the pose angle, because the destination is somewhere here. Same thing, all of them are pointed sideways in order to make the challenge great. So you're not allowed to pivot and go because that's the easy way to do it, but it's not optimal. So you find the robots going forward and turning. And she has come up with an algorithm to create the best trajectories. Watch, 2 of them almost hit each other. It's not luck, because she has designed the trajectory so that they can come within a certain distance of each other, because otherwise it won't be optimal. So you want the robots to flow freely. So that's what she has done. So there'll be 2 near misses, except it's not near misses because she's planned the trajectory. See that right there? Very close. And very close there too. But it's actually planned. And then they'll turn again. No stop and turn. They turn on the move. This one turns all the way around. Let's watch it one more time. So they almost hit each other, but it's planned, so there's no danger. So this is what the robots do on Amazon. They go back and forth all day. Alright, so there's one other thing I wanted to show you before we get started. And that is this particular application which I found last week. Now this is very relevant to you, medical robotics students, so watch carefully and then we can have a discussion.
Rewire nerves, so when the patient tries to do movements with his missing hand, those new muscular structures get activated and then put electrodes inside them, so we can extract that information. We use an artificial intelligence algorithm to look at those electrical pulses that come from all the different sources and learn what is the patient trying to do. And once it's learned, which happens very quickly, then you can tell the prosthesis what to do. one of the important parts of our work on translational research is not only to show that something is possible, but to communicate it so other people can use it. Those are ongoing efforts, and we hope that we can bring this technology to more people relatively soon.
So, do you understand what's going on? Because people who have their hands amputated above the elbow, there's not enough muscles left to be able to control the prosthetic. So they actually transfer muscles from some other part of the body, and then they put electrodes there, and those muscles are capable of doing what the lower hand would have done. So they pick up the signals, and then they get the robotic hand to activate. So it's very cutting edge research in medical robotics, obviously. So we were talking about localization and mapping, and here is a very practical example that probably most people would not have thought of when they think of localization and mapping. You always think of robots that look different, like the ones you've seen in movies. So this is quite a recent article, only like 3 years ago. So essentially, this company is testing vacuum cleaners. You heard of the Roomba, right? It's a vacuum cleaner, the original vacuum cleaner, automated vacuum cleaner, about $600, $700. So most people would not buy it. Like, who would buy a vacuum cleaner for $700 when you can get something for $200? So it is autonomous. It goes around the living room. So when somebody leaves for work, you can just turn it on and it will clean the rooms on a certain floor. I don't think it's capable of climbing stairs. And then it will shut itself off. It even recharges its battery. It knows exactly where to go and recharges the battery. So essentially he compared many different vacuum cleaners, and he's shown the pattern of coverage. So some of them are total fraud. They charge a lot of money, and the white area right here is the pattern of coverage. So notice, it's because when it bumps into something, the way you change its direction has to be comprehensive, But if it's predictable, then this is what you'll get. You get these little circles, and you have a lot of circles and empty spaces in between. So obviously it's not doing much, right, in terms of coverage. So both localization and mapping are involved here, because you have to have an idea of the living room, and then you have to know where you are in it. So you have to have a map of the living room, which you build up, and then you have to localize yourself. And now you'll see other vacuum cleaners which get better and better. So these are the vacuum cleaners that were tested. And here's a slightly better one, but still lots of space, empty spaces that have not been cleaned. So a little bit better, So there's furniture there, right? When you have furniture, you have a problem. Human beings can move the furniture, or they know exactly how to go around the corner of the furniture. The robot is not that good at doing that. So that's where it hasn't done much here, because there's so much furniture. Too spotty. One in. Getting much better. So obviously their localization and mapping method is better. Use laser navigation, some of them at SLAM, which we got into. So essentially it uses that to walk around the room. And see, it's going underneath the tables. Many of them will avoid that area completely, because they use a bump sensor, and it will move it, touch it, it will reverse. But this one seems to be able to find the holes and go in there. Not so good? Excellent. Look at this one. So when you leave today, go and buy one of these. Neato Bot 536, if it's available. So it's getting better and better. So, nice article. Because it shows you why localization and mapping is important. Now, earlier on, in the very first class, we talked about nanobots. I tried to connect it to medical robots. So they have these little tiny robots, right? Do you remember that? Or it's too far in the past. That you inject into the bloodstream. And the blood vessels are 60,000 miles. I have to check the number because it seems too high. 60,000 miles of blood vessels in our body. So you can imagine that there will be localization and mapping needs inside the blood vessels, because they have to find their way to wherever it is they're supposed to either deliver a drug or do some microsurgery or whatever, right? So you have to have a localization and mapping plan. And you're not going to use just one nanobot. There might be like 10,000 of them. So there has to be some traffic management and so on. So all these robotics principles, they are applicable even in that situation. So still, I think even with the coverage, $600, $700 is too much for these vacuum cleaners, because a human being will just spend half an hour and you save $700 and you get some exercise in the process. Okay, so yeah.
You mentioned nanorobots, right? So I have a question. In case there is a nanobot that is being built and they have to simulate it, test it, so would we still be using ROS?
So I believe the software to move it and all that will still be ROS. The simulator will have to be special, because the simulator is supposed to create a reasonable copy of the actual environment, right? So they'll have to create a reasonable copy of the inside of a person. So you'll need a special. Remember, gazebo is no longer part of the ROS grouping. It's on its own. So they'll probably have special purpose simulators that capture the inside of the body in some way.
So there are simulators about gazebo which are specifically for medical purposes?
I don't know of them, but I bet you if you Google it, you might be able to find it. I do know that there are special purpose simulators that the auto company uses for regular cars, and those things are private. They will not, you cannot use it unless you're an employee working for them, because they've developed it themselves, and they're very nice. They actually can simulate wet roads. They can drive the car on a wet road and on snow and so on. Those simulators are probably millions of dollars.
When you do this localization path planning, what is the resolution which you can expect?
So that's determined by how you implement the algorithm. Typically, you don't want a resolution any bigger than the robot. So if the robot fits on this tile, you only want this resolution, because beyond that it's
I'm
not.
talking about, suppose it is a medical robot which is used for the surgery.
Yeah, then you'll probably get down to micrometers or something.
Okay.
You'll get down to a very small resolution, which is appropriate to the application.
Okay.
Yeah.
Is it possible to get micrometer, because the needle dimension is decided about what is the maximum which can penetrate, and then
Yeah.
if it is a for surgery.
Right. So that's the frontier right now,
Okay.
because they have some robots right now that do knee surgery.
Okay.
I'm very curious to see how they do it. There must be a human being there, because you can't be operating on the wrong part of the knee. So I think it's assisted.
Mostly assisted.
Yeah, right. So it'll
Even
get
assisted
better.
robot, because even
Yeah.
the assistant may not be, I think, on contact, because they'll be assisting through the image.
Yeah. Yeah, right.
Yeah.
So like all these things, you start with something that. So we saw some of the robots in the first class that it was trying to do surgery. It was scratching like a cardboard surface. But unless you check out the resolution, that might be just show, right? They're showing, a robot scratching a surface, and they say, okay, I have a force sensor, so it's not going to, use more force.
The same question she asked,
Yeah.
same.
Yeah.
Is there any similarity? Because you know that what is the amount of force required to cut the skin? What is the amount of
Yeah.
force required to cut this muscle?
Right, right.
So before we implement itself, we should have some type of simulation.
Yeah, right. And you also need the very delicate force sensors.
Okay.
Yeah. So, but you have to start somewhere, as I said, right? I mean, ISRO did land on the moon in a couple of days. They had a couple of trials, failures, and and gradually they did it. So, technological progress is very incremental.
So, sorry, another.
That's okay, no problem.
So, in the gazebo environment, right? So, is it possible to integrate our own, say, design 3D models or something? Suppose we're
Yeah.
very specific about how we want the robot to move or where it goes, the environment. While we're creating the world,
Yeah.
is it possible that we design our own 3D model of some objects in the world
Yeah.
and then place them in the gazebo?
Yeah.
And then see how that's
Yeah. So the robot models that you see for Turtlebot 3, they are created in a CAD environment.
Okay.
And apparently, the standard CAD, whatever the format is, because I'm not a CAD person, that can be imported into Gazebo. So they allow it to be imported with standard CAD drawing packages. It's not AutoCAD, it's some more elevated thing that open source people use. AutoCAD is you have to pay money for. So open source guys will never use anything that you have to pay money for. But there are documents that tell you how to draw it and what format to use, and it can be brought in. So even the robots you saw they started with a CAD model. And that's how they're able to copy, reasonably, because you saw the Turtlebot 3 the other day. Lesson had brought it here, right? There's no need to capture the intricacies of, every single little detail, right? Because that's not relevant to its motion. So CAD, it simplifies that, it abstracts it, and then you can import it and it becomes a model. There is a process described in ROS how to do it. So we've tried some very simple robots, with very simple geometries, and it works, You can give it a color, the wheels can be different color from the body and so on. So it is in the gazebo document, how exactly you do that, which language to use and so on. Okay, so there is still not enough people, because I was going to discuss how to do the second exercise, which is due tomorrow. I'm going to start grading the first one. So this is the program that you're going to modify, right? So let's quickly go through the parts of this program. So don't get intimidated by the standard stuff, setting up ROS and so on. You're just going to copy automatically all the publishers and the robot has a tendency to move even before you give it commands. Resetting it, all that you can just copy blindly. There's no need to worry about that. Then creating the publisher, etc., etc. The real action begins somewhere here. So some of these you may not need because you're doing it in a different way now. You're going to the waypoint, not on a triangle. So you might have to set up the waypoints here with a different name. So all those are details, okay? Now, this is where the main part begins. So here is a for ns is equal to 1,3. So this will be your number of waypoints loop. So it will cover everything, top to bottom. So if you have 3 waypoints, you do it 3 times. So you can, once you get it working, you can try it out with other waypoints, 4, 5, 6, All right, now, so you'll have a loop to see whether you made it inside a circle with radius, I think I said 0.02 meters, around the waypoint. So this first loop, the while loop, will check whether the distance to the next waypoint, you know how to calculate the distance to the next waypoint? It's a Euclidean distance, right? You keep checking and see whether you're within 0.02 meters. At that point, what should you do? You have to get out of this outer loop. There is an inner loop, I'm going to get to that. You have to get out of this outer loop and do the next iteration of the for. Is that clear? You have to replace the current waypoint by the next waypoint. And if you use the right symbols, the for loop will take care of it. Just make sure that it goes to the next one, right? That's why you can use this index here. Here, NS. In this case it's NS, you can call it waypoints WP or something. And you kick out of this and go to the next one. Now, within this loop, there's going to be another loop. And that loop is going to direct the robot to turn towards the waypoint always. Once is not enough, because as you move, I told you, the gazebo has some noise that they add. So even if when you're driving, is it enough to set the heading and then just forget about it? No, you have to constantly steer. So within that inner loop, you have to constantly steer, right? By the way, let me go back to this loop. Well, those things I can say later because I'm going to go to the board. You have a pen, right?
Yeah.
Okay. The inner loop is going to control the heading. Now, the other 2 things I want to remind you is that there are 2 programs. One was to convert from Euler to quaternion. You need that. The bigger one is how to calculate the heading in the robotic angle system. You remember that? That includes unwrapping. So I can go back over that, but first I want to go to the board and talk out the algorithm for you. Now, yeah, let's do that on the board. So that's my working program. It's about 179 lines, no pictures. So it's about 179 lines. Most of it is comments. I love to write comments, right? Okay, enough. You don't want to see that anymore. So you don't want, most of it is comments. It's not 180 lines of program. I like to write a lot of comments because I forget very quickly. So next week I won't know what happened in the program unless I look at the comments. All right. So So this is OLCL2. Remember the other two programs, and now you can turn it off. Okay, now, so here you have the for number of waypoints, and the end of that is somewhere here. While not reached next waypoint. Got it? And that goes from here to here. And then somewhere here there is while not pointing next waypoint, and that goes from here to here. Is that clear? So, if you're not able to get it to work, there is some implementation issue. It's not that this idea is wrong, it's just that you have to implement it correctly. So, how are you testing this? The computer doesn't understand English, so you can't say while not reached next waypoint within 0.02 meters. It will say, what are you talking about? I don't know. So, somewhere here the distance has to be updated, right? Because otherwise it still thinks you are at the starting point. So if you miss that, you're going to get a problem. It's not the algorithm, you haven't implemented it properly. The computer is a stupid machine. So you have to make it intelligent. So you have to update distance here. Update distance to waypoint. Now MATLAB has this interactive mode. So you can see if the distance is not changing, you have not updated it. Quite simply, it will never trip this condition, never, if you don't update the distance. So let the distance be printed out, and then you realize that you've forgotten to update the distance. How will you update the distance? You have to update the position of the robot, otherwise you'll get the same distance, right? How do you do that? Then go down. So update distance to waypoint. First you got to refresh ODOM. Does that make sense? So it's purely logical. If you don't refresh the ODOM, you'll be getting the same distance, right? But the robot is moving. You can see it in the gazebo. So how come the distance is not, getting updated? Because you may not have refreshed ODOM. Now, how do you use the ODOM? We've got the piece of code. You don't have to reinvent that. Just we've done it so many times, right? And how to put it into the X and Y plotting variables. That's blind copying from OLCL 2 or 1, 2, I don't know. So that we blindly copy, right? Okay, now this is the more difficult loop. While not pointing to next waypoint, right? Within how much? I believe we said 0.2 degrees? No, 2 degrees, right? 2 degrees. Don't mix up radians and degrees. The computer cannot overcome that fault. It thinks that that's what you want. So you have to do the conversions. Why are we working in degrees? It's because it's easier for us to figure out what's going on. Quaternions, radius you might be able to understand. Quaternion is not a chance. Just by looking at it, we will not be able to understand it. So therefore, we work in degrees only because it's convenient, but then there's radians and there's quaternions. So you have to use the appropriate representation. So while not pointing to next waypoint, right? What do you need to update here? You need to calculate current heading, right? Right? So how do you calculate the current heading? Again, the ODOM, the quaternions has that information. So if you don't refresh the ODOM, you won't get a new heading, right? You won't get a new current heading. Is that okay? Let me repeat that. Calculate the current heading. Calculate the current heading means you need to know the current orientation of the robot. For that you have to refresh ODOM, get the quaternion out. And that's why the other program helps. We've done it there, right? Remember we did that? Separate program, simple program just to get the heading out. So you have to copy that in and get the current heading out. Don't mix up, again, I don't mind saying this over and over again. Don't mix up quaternions, radians and degrees. So, you've got the current heading, right? But the desired heading is also changing because the robot is not sitting there. It's moving, it might go like this, it might go like this. So even though that point is fixed, actually you can do this even for a moving target, you know. But shall we change the assignment and make it a moving target? No. It's too late now. But this heading is changing because, you know, you're moving. So every time you have to use another program where I say calculate heading. So remember the lessons learned in that. The heading has to be obtained using atan 2D, I believe. That's in degrees, but not only is it in degrees, it's from minus 180 back this way to 180. You don't want to go from 0 to 360. You definitely don't want to get radians there because you have made up your mind that you want degrees for human understanding. So suddenly don't go to the radians because it'll be very confusing. Right? At the last step, well, we haven't got to the last step yet. So I calculate the current heading. I just told you verbally what you need to do. Then you need to calculate the theta error, which is, okay, let's call it heading error. I believe it should be current minus desired. This is very important because if you define it the other way around, desired minus current, you know what's going to happen, right? That Kp might have to, the sign might have to be flipped. So, you know, I never remember these things. I try to see what's going on there and figure it out. You know, there's no point in memorizing these things because there's only so much room in my head, particularly as you get older. So you try to get rid of all the extra stuff. So, whatever it is, I think it's this one. I think so. So calculate the heading, right? It's still going to be in degrees, right? Because you worked in degrees. So this is like your error that you want to correct. And how are you going to correct it? Because you're going to give it a new, see, we've decided we're not going to change the forward velocity. You know what would be nice? As you approach the waypoint, you want to slow down. That's what we do when we approach the house, our house, you know, we slow down. I said, let's make this simple. So let's set a small, let's say 0.2 meters per second velocity and, you know, let it go. Okay? So over here, omega has to be set. So omega is equal to Kp. Computers don't do subscripts, but I like writing it as Kp, proportional constant, times this one, heading error. Did I define heading error? No. This is heading error. This is the alternate which doesn't work, or is the wrong way of defining it. So heading error, is that okay? So Kp times heading error. So this number, I initially went with 1 and the robot started doing this. And I ended up at around 0.01. You can try different numbers. So don't spend the entire day searching for the right value. I gave you a target. You know, it's about 1/100th of 1. And that seems to work. And then you can try making it, I didn't try to tune it anymore. Right? If you put 1, it's going out of control, right? But maybe if you make it 0.1, it might go like this, right? Some people don't like that. They think it's normal, right? It's all a matter of preference, right? So you can try different values, right? If you make it too small, let's say you make it 0.001, you're going like this. And that's not good also, because you want to correct reasonably fast, you don't want to overcorrect. That's the significance of this number. You have to do it by trial and error because we're not going to inject formal control theory into this, right? In controls, there are ways of obtaining values for this in the optimal manner. Here, we just want the program working. Is that okay? Alright, so you apply this correction. Now, if you just do this and say, how come the robot is not correcting? It's because you still need to do the bookkeeping. You need to push this into the VEL MSG and send it to the robot. If you miss that, you'll say, oh, this method is all wrong, you know. Like this professor doesn't know anything he's talking about. You know what I mean? No, because you haven't told the robot that this is my new velocity. You get it for me? So, ask questions. Do you understand? So, the result can never be achieved like this. You write code for 5 minutes and then it's done and then you go for lunch. It is incremental. And the more practice you have, the better you get at it. people who program for Microsoft, they are mostly from India. They are very, very good. They measure their skill by so many hundreds of lines of code in an hour. They're very fast. They don't have to look up help files and so on. It's all in the head. So the point is, little bit at a time, debug as you go. Just ask, is this the correct heading from where the robot is sitting? And don't forget to convert the heading back into the appropriate format. Here it has to be radians. I'm sorry, I forgot to tell you that. Here, this is in radians per second, right? Because the robot only takes commands in radians per second, not in degrees per second. So obviously, whatever you did here, it has to be converted to radians, not to quaternions. Convert to radians. Does that make sense? If you miss that step, it won't work. And it won't be the fault of the method. It'll be you haven't coded it properly. So MATLAB is beautiful because you can you can block 3 or 4 lines of code and say, implement this in the workspace below. And so it'll tell you what the result of this. You can set a test. Do I know how to do this? And then once you're happy with that, you can put it into the main code. C++ does not allow you to do that. C++, you'll have to get a printout, and then you have to look at the printout, the program is finished, and then you have to go and edit it. MATLAB is interactive.
When we calculate omega, that is kp into heading error, so that is calculated in degrees, and then we convert that to radians.
Yeah, you could have calculated from radians from the beginning, but then you won't be able to appreciate those other values that you might need for debugging. Because this is the last stop. You have to convert here back, because it's not going to accept degrees. So keep everything that you are going to view at degrees, and then wherever it needs radians, it's not going to change. You have to change for it. Yeah.
In the open loop code initially, so we provide the length of the side of the triangle, right?
So it's not relevant anymore.
Right.
Because you're just calculating the Euclidean distance and you're trying to bring it to within point 2, right? Point 2. You're trying to reduce it. So this is exactly the way we drive. Because if I'm not pointed at the waypoint, that distance will never become less than 0.2. How will you be lucky? Yes. If your robot already happens to be pointed in the general direction, you might get lucky. You run it again. Remember the robot weird sometimes? That's it. You're going off and off and off, and the distance is becoming bigger and bigger and bigger, and that's it. The robot will be gone. You go around the earth as you go.
We can provide the waypoints in a single array.
Yeah.
We have 2 different arrays for x and y. So we need one like x from here, y from here, and we have a single array of.
Yeah. So the way I did it is, I had x and y separate.
Yeah.
Some people can have like a 1/2 and do it that way. If you have done that, when you plot it, you have to make sure that you pick the right things for the plot, right? So I like, I'm old-fashioned. I like to see x and y. Some people do it in 1/2 matrix. There are some excellent MATLAB programs that I have seen. What I do in about 6 or 7 lines of code, they will do in 1 line of code. They are able to do that. But I like clarity. When you do that, 5 steps buried in one, you don't understand your program afterwards. So I prefer to write it out and write comments and do it slowly, because then the program is understandable like even a year after you've written it. So, any questions?
In the open loop code, there is something called log term is equal to pi/10. What is that?
Yeah, okay. So I have, just like I chose a forward velocity of 0.2 or maybe 0.4 meters per second, I chose a rotation rate of pi/10. That seemed reasonable to me. Pi radius is 180 degrees. Divide by 10 is 18 degrees. So I'm saying 18, I'm going to set the turn rate. Whenever I need a turn, I'm going to set it as 180 divided by 10, 18 degrees. That was for that. Here, you can pick an initial omega at the top, you can make it pi/10, but later on it's going to be determined by this equation. So unlike that program, it's not a fixed turn rate. Initially I chose something. Actually, initially I think I put 0. You can make it 0. You know why? Who can tell me why? Unlike the sample program, you can make it 0 instead of pi/10. Because the waypoint is here. right? I don't know what the waypoint is. Why should I make it pi over 10? Maybe it's minus pi over 10. So the best thing is, say, let me go forward a little bit, and in that time I'll calculate where the heading is. Right? It'll correct it. So maybe you should just say start. Just start. Move. And then you do a heading calculation and you start to turn in the right direction. So I'm glad you asked, because we don't want to lock ourselves into pi by 10. That seemed reasonable for doing a triangle, because I know the robot is pointed at the, at the next waypoint. And initially I make it 0. I don't make it pi. I make it pi over 10 only when I reach that and turn towards the next vertex, right? So it's a different context entirely. None of those numbers are sacred. You can change it according to this. So if you focus that way and write small segments of code, for loop, 2 while loops inside, do all the corrections needed, quaternions, refresh the ODOM, calculate the heading properly like I suggested, it'll work. I gave away part of it because I said don't be searching, Maybe some people will say 1, let's go to 10. No, if it's becoming unstable, it means this number is too high, because a large number is multiplying this error and producing like. So the robot says, okay, if you want me to do that, I'll do that up to the limit of the turtle bot's 3x capacity. That's what it's doing. And it's becoming unstable because it's a physics model. So that is running on the basis of a physics model. So it's great that it's copying that ability of instability. Because if you spin a robot like that at high speeds, it can't fall over. Do you notice when you stop it, it seems to go like this? So that's because of the way they programmed it, because it's almost as if one tire or one brake is different from the other one. So why doesn't it sometimes go this way? I think they shouldn't have done it to bias it one way, because do all the turtle bots have one back brake? They don't use a physical brake. The motor is being, but one motor comes to 0. You remember our discussion? If you stop the left wheel and the right wheel is still moving, you go like this. That's what is happening on the stop. So I'm wondering why they are stopping one motor before the other. And I have to believe this. Remember our discussion on the figure of 8? It could be that one is spinning more than the other, and therefore you can get the left motor stopped earlier, and so you get this. Maybe if you did the circle the other way around and stopped it, it's a good thing to try. If you're going the other way, maybe it'll stop and go this way, because the other wheel will now be going faster. Slow. When you speed up, you're really not gaining time. You will find that in most algorithm design, when you go fast, you end up by spending much more time later, right? You think you can get it done. Maybe when you get more practice, you can increase your speed. So once you get it working, put waypoints all over the place. Maybe it's a loop running 5 times now, 5 waypoints, with the last one always being the starting position. So make it go like this, That's why I made the first waypoint here, because if I make it here, there will be an easier initial move. So I wanted you to face away and then again face, reverse your direction and then come back here. So there are programs that can get the robot to park at 0, 0 with any heading you want. We did not do that because we don't want to complicate the problem.